An encoder is a device that is used in many industries to provide feedback. In the most basic terms, an encoder, regardless of the type, which we will cover later, senses position, direction, speed, or counts. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealParse videos. This way, you never miss another one. Encoders will use motion under a variety of technologies and translate it into an electrical signal. That signal is then sent back to a controlling device, such as a PLC, and is interpreted, meaning scaled, to represent a value that will then be used within the program. Some of the technologies involved in encoders are magnetic, mechanical, resistive, and optical. Optical is the most widely used encoder motion translating technology. There are different types of encoders, such as absolute and incremental. We will describe those in greater detail in a future lesson. But for now, an example of an incremental optical type encoder uses a beam of light that passes through a disk that has opaque lines in a specific pattern, somewhat like the spokes of a wheel. On the other side of the disk is a photosensing device that will interpret the light based on the pattern on the disk. Picture a shutter blocking and unblocking the light. The pulses of light are then converted to an electrical signal to be sent back to the processor through the encoder's output. Encoders have a wide range of uses, which include closed-loop applications such as servo or VFD control, measuring, and counts. Here are some examples of processes that may use an encoder. For VFD control, you may be running a pump on a VFD to fill a tank full of a liquid. You are requesting a certain speed and want to verify that the pump's VFD is at the requested speed. An encoder on the VFD may be used for feedback of speed. Next, let's give an example for a measuring process. In this application, you will need to cut some aluminum product to a particular size. You are passing a long roll, meaning hundreds of feet, of the aluminum sheet through a cutting mechanism. You need to determine the amount of aluminum fed so that you can cut the sheets to the proper size that will be used in a separate manufacturing process. An encoder, attached to the conveyor and reading the material that is feeding through your cutting assembly, will indicate the length of material that has been fed since the last cut. That feedback can then be used to adjust the cutting blade to sever the length required. For an example of counts, consider this process. You have a conveyor line that has bottles running on a conveyor. They are counted by a photo eye sensor when entering the assembly. They have a cap with an aluminum tamper-proof foil on top that needs to adhere to the bottle. Once the foil is sealed, the bottle will then move down the conveyor line and verified that it exited the cap sealing assembly via an exit photo eye sensor. Some of the requirements for this station are: the same number of bottles that enter the assembly must exit in a predetermined time frame. The bottle must not remain in front of an entrance or exit sensor. The bottle must not be exposed to the inductive sealer longer than a predetermined amount of time. You must make this assembly flexible enough to handle many types of bottles and entrance and exit sensor placement. Consider a prescription bottle. Easy, right? No handles, just a bottle that is a standard size. Now, consider an antifreeze bottle with a somewhat small cap and a very large handle. How in the world are you going to meet the requirements for the machine and remain flexible? If you put a pill bottle in, yep, easy peasy, right? Bottle in, seal, bottle out, no sensors blocked. If any of the requirements fail, bottle in, seal, tips over and isn't counted out, machine halts and alerts on operator of a malfunction. How about the antifreeze bottle? Bottle in, cap passes in front of an entrance sensor, bottle counted, then the handle. The system faults because it sees a blockage at the entrance. How do you tell the machine that this is expected behavior? An encoder, of course, and a selector switch for a setup mode. To set up, insert your product, in this case the antifreeze bottle. You make sure to feed cap first, and it must contain a foil. Your program reads an entrance on the sensor and records an encoder reading, as well as determines that this is a cap and records that fact. Your program then reads another entrance and determines that this is not cap and must be some other acceptable part of the bottle, possibly a handle. The single bottle continues down the line, where the exit sensor is triggered. At that point, you again record the encoder value. You now have an encoder count that registered at the entrance and exit. In the code, you subtract the entrance from the exit, and you have a bottle count. You now know precisely how long it will take that bottle to move through the system, meeting the must enter and exit in a predetermined time frame, in this case, encoder counts. You have also made the flexibility aspect of different types of bottles, as well as being able to place the entrance and exit sensors any reasonable distance apart. When back in run mode, the code knows that there's a handle to ignore when it comes into the process, and doesn't fault the machine. You register the encoder at each bottle entrance and predetermine when the bottle must exit. If the bottle doesn't exit the machine in a timely manner, which is based on your projection and the current encoder count, the machine faults. This is a great use of an encoder that is fully configurable. Count in, count out, subtract, done. Don't miss the next lesson, where we are going to discuss incremental and absolute encoders. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.